Right, had a request for a quick explanation about reactions between metals and water. Thought I might as well just do a quick video in case it helps anybody else as well. Ultimately, for a metal to be able to react with water, it needs to be above hydrogen on the reactivity series. And if that's the case, there might be a few other sort of limitations. I'll talk about that later on as a bit of extension. But ultimately, the products are always the gas, hydrogen, and a metal hydroxide. Okay, so the classic demonstration of this is with the group 1 metals, where we put them in order of reactivity. You know, you look at these 3 elements: lithium, sodium, potassium. We conclude that potassium is more reactive because it's a more vigorous reaction and catches fire and whatnot. And then we go on to talk about shielding and why the group 1 elements get more reactive down the group. But let's use these group 1 elements first, and I'll just extend it one step further. So I'm going to pick on potassium. Okay. It reacts with water. Now, this is a displacement reaction, okay? What happens, in effect, is that the potassium takes the place of hydrogen in this oxide, in H2O. However, we don't get potassium oxide and hydrogen, we get a metal hydroxide and hydrogen. That's because this is all happening in excess of H2O. So first of all, just take it at face value, that's what we get. We'll look at why in a second in case that helps. So I don't want to overcook it for even a revision. You know, we want as much detail as we can. So there's a metal hydroxide. Whoops, fail. There's hydrogen. Now it's H2. Don't forget we're talking about the element here. That's a gas. I'm going to put some state symbols on these. Solid metal, liquid water. This is soluble and so is aqueous in the bulk water that hasn't reacted. So for every water that reacts, there are many, many other H2Os which are just there being the liquid into which the reactants dissolve and the products form. That effervesces, that's the gas, which if we tried to light it using a lit splint, we'd get a squeaky pop out of a test tube, okay? It's not balanced, I'll quickly balance it. It's currently balanced in terms of O. I've got an even number of hydrogens here and an odd number there. So I'm going to make it an even number on both sides. So now I've got 4 hydrogens, which means I need 2 waters. That also deals with the fact I needed 2 O's off the back of that, 2 potassiums, there we are. And we could copy paste that, just swap out this for a different group 1 element, lithium or sodium, and you get the same thing. Now, just to go as deep into this as we possibly can, what we have in potassium hydroxide here is obviously a compound. It's got more than 1 element combined. We know that hydroxides contain OH minus ions, and being a group 1 element, that's K plus. So the correct formula for potassium hydroxide is, as it's written there, KOH. All capital letters, because those are 3 elements: potassium and oxygen and hydrogen. We know that it's this ion here, the hydroxide ion, which causes alkalinity. Now, a question that I've been asked once upon a time by a student, there was some confusion. They were saying, hang on, shouldn't it go acidic because hydrogen's formed? And that student, I think, must have been thinking H plus ions, which are the ions which cause acidity. But that's not what we're getting in this reaction. We're getting the element hydrogen rather than H plus ions. So H plus ions just aren't here. So this would be a pH neutral solution. Basically, the H2O is pH neutral, pH 7, and the pH goes up because, well, it becomes alkaline on account of those ions forming, okay? Now, let's just take it 2 little steps further. First of all, I'm going to use 2 different metals now, just to demonstrate the balancing. And then I'm going to go a step further still and talk about redox and electron transfer and half equations, which is as far into this as we could possibly go. So these 2 elements are also sufficiently reactive to displace hydrogen from water. Again, we don't get magnesium oxide and aluminium oxide from hydrogen oxide. Again, because it's happening in water, we end up with a hydroxide. It's probably best just to trust on that one. I can go deeper into it. If I remember at the end of the video, I will, but it's going a bit too far. So again, we get a metal hydroxide plus hydrogen. So the game here is, remember that pattern, that if it's more reactive than hydrogen, then they go. However fast or slow the reactions might be here. And then it's working out the formula. So because magnesium's obviously in group 2, it gets its full outer shell by shedding both of its outer shell electrons. It has 2 of them, and makes an Mg2 plus ion. So we'll end up with Mg2 plus. You can see there's some electron transfer there. We'll come to the redox in the last part of this short video. Hydroxides are OH minus, so we need 2 of them. We use brackets because the OH is more than 1 atom, and there are multiples of it. There we are. Again, it needs a quick bit of balancing. 2 O's, so let's have 2 waters. And then that does it actually. I've got 4 hydrogens, 1, 2, 3, 4 hydrogens. You'll see this every time that two waters are consumed in the reaction to make one H2 molecule. It's basically as if each of these H2Os is being split into a H and an OH. I'm going to be a bit vague about ions at this point because we could look at it as if it were H plus that gets displaced out as H2. But it gets split, so each water loses a H and they pair up to make H2. Again, I will say more on redox in a sec. What would the formula of aluminium hydroxide be then? Well, again, a bit of essential knowledge. It's a group 3 element, and it's a metal at that, so it forms positive ions being a metal. It forms 3 plus ions being a group 3 metal. 3 electrons lost to get a full out shell. So we'll need 3 hydroxides to balance the charge. So the formula for aluminium hydroxide is that. So this time the balancing will be a bit different. You'll still see this 2-to-1 ratio here though. Okay, watch this. So we're going to be a bit cheeky because I know where this is going. I don't want to half in my equation later on. So I'm just going to casually double that. That's maybe not the first and obvious thing to do. Maybe I should have put a 3 there because of 3 O's. But I foresee a half coming in and I'm just trying to bypass that now. However, if you want to just balance it yourself at this point, maybe without putting that 2 there, by all means pause it and go ahead. Anyway, having done that, I've now got 6 oxygens, so that'll be 6 H2Os there. Aluminiums, I've got 2 aluminiums, so just commit to a 2 there. Let's check the H's then. I've got 12 H's in total, 6 of which are there. So the other 6 hydrogens are here, which means 3 H2s. And again, it's not the most obvious thing, but there's a 2-to-1 ratio there. That's because 2 H2Os are becoming 2 OH minuses and a hydrogen. And you can see that's not balanced in terms of charge. It's because there are some electrons being handed over. I wouldn't expect you to look at that and say, oh yeah, obviously. Okay, by the way, don't worry. But that would make sense. Now, as it goes, this reaction is mega slow because aluminium as a metal has a really thin, very, very strongly bonded oxide layer on its surface. So aluminium foil at home doesn't spontaneously combust in contact with oxygen. It doesn't dissolve into water and make an alkaline solution and a flammable gas. If it gets a splash of water on it in the kitchen or whatever, aluminium foil is aluminium, but it's coated in this oxide layer that actually makes it pretty impervious to anything that comes along. But aluminium does react with water if you give it a chance, okay? Now, that might be enough for you. That might have answered the question if you had one about what's this all about, metals plus water. I would go back to the Group 1 reference for a sec and say the usefulness of this on the GCSE spec primarily is in putting the Group 1 elements in order of reactivity by looking at how vigorous the reactions are. We could measure the temperature change, we could just measure the volume of gas produced per second. Generally it's a more intense reaction with a faster rate of reaction. Might get a bit noisy in the background because it's break now. There's some squeaky year 7s running down the corridor in a second. If you're still with me then, the last thing to talk about is the redox side of this. So let's go back to the potassium reaction. There's quite an awkward half equation in here somewhere. And I will tackle it, okay? Don't be put off if you're like, oh, this is a bit much, okay? So in terms of redox, we've got these potassium atoms becoming potassium ions there. We can tell that again just by picking apart that formula, using a bit of general knowledge. That's a hydroxide, it's alkaline, so it must be K+. How does a K atom become a K+ ion? Well, it loses an electron, okay? Now let's try and piece together the rest of this. This half equation appeared earlier on, just a second ago on the previous side of this page. So the other reaction must be where water somehow turns into H2, okay? I'm going to go and regenerate that half equation that I flashed up and says, don't worry if that's a bit tricky. Let's use a bit of logic to work out how this might work, how this plays out. So the story goes that a water molecule somehow gets split in the process of this reaction, becoming a H and an OH. Now I'm being really cavalier here because we do need charges, so I need to deal with them now. We know from just learning the content that that's a hydroxide ion, okay? And so actually we could consider the H to be a H+ ion. Again though, that goes back to the point that there's no H+ here, there's the gas hydrogen. So what we could see this as, don't worry if you don't quite follow this bit, is that the two waters are in effect 2 H+ ions. And that those 2 H+ ions get given an electron each to become a H atom, and those 2 H atoms pair up to make a hydrogen molecule. That's one way of sort of looking at what happens here. That's really not obvious, so don't worry if at this stage now in your revision you're like, what? This is news to me. I'm pointing out that it's tricky, but there's a way of sort of tackling it, or a way to look at it. At the end of the day, you might just take it for face value that you just get hydrogen, and you don't need to worry about why exactly or how that works. Anyway, we do know that these OH minus ions are a thing, and for every H2O gives out one H atom. So for two waters, there would be two hydroxides. Okay, just based on the fact that the O has to balance, and I know that it's metal hydroxide that's formed here, so that's where the O goes into that hydroxide ion. Now when I look at that, that's balanced. I've got 4 H's and 2 O's, 4 H's and 2 O's, but the charges don't balance. And again, the year 12s would have a better job on this one, so I don't want to overdo it. Basically, the only thing that's left to do is put some negative charges in. Somehow these H2Os become OH minuses. There must be some negative charge coming from somewhere, and it would follow that it's 2 electrons. Okay, so that is a really, 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 certainly from a GCSE perspective, but even beyond this level, like awkward half equation, because it's not a straightforward like, yeah, there's a metal and it loses some electrons and becomes a positive ion, and however many charges it gains, that's how many electrons it lost. It's not as straightforward as that. Now that does make sense because these potassium atoms, there are 2 of them, they're each releasing an electron to become their K plus full outer shell form. So 2 Ks come along, they become a K plus each. There's that, look, 2 Ks becoming 2 K pluses and shedding 2 electrons. And those electrons have to go somewhere. It seems to be that the water, the only other reactant, must be the thing, or things, the 2 of them, which accept those electrons. And when those waters take those electrons in, however that works, they end up as a hydrogen molecule and 2 OH minus ions. Okay? Anyway, that's as much as we could say. I suppose actually, having said that, as always, here we've got electrons being lost, so that's reduction. No, it isn't, sorry, it's oxidation, oil rig. Sorry folks, yes, it's definitely oxidation, it's going up in charge, it's losing electrons. Reduction is gain of electrons. Here we've got water gaining electrons, apparently, and so there we are. Excuse all the scribbles, there we are. I hope that's somewhat helpful. Copper just doesn't react with water. Evidence for that is copper pipes that our hot water flows through, because copper is just less reactive than hydrogen. But if it's above H on the reactivity series, it will react with water. And if it does, as and when, it's always following this format. Okay. Anyway, I hope that's been helpful. Good luck.